Hello, welcome to Econometrics Melody. In this video, we'll discuss about the Weibull distribution. Let us see some of the useful functions. This is how we can calculate e to the power something, Euler number to the power something. Euler number to the power 1 is equals to the Euler number itself, and the Euler number to the power minus 1 is equals to its reciprocal. E to the power minus 12 is this small number 0. Now let us see another useful functions, natural logarithm. In natural logarithm, the base is the Euler number itself, and let us calculate the value of natural logarithm. We cannot calculate the natural logarithm of 0. Natural logarithm of 1 is 0 because e to the power 0 is equals to 1, and the natural logarithm of the base, that is the Euler number, is 1. As exponential and logarithm are inverse to each other, that is why in such case we get the result is the input itself. Now in next example, by the help of these functions, let us establish the relationship of gamma and factorial. Gamma n is equals to n minus 1 factorial, therefore gamma 12 is equals to 11 factorial, gamma 6 is equals to 5 factorial. We cannot calculate the factorial of decimal numbers, while we can calculate the gamma of decimal numbers. Now let us see some of the useful formulae of the Weibull distribution, and we will explain them. So Weibull distribution is the function of three parameters: a shape parameter, b is equals to scale parameter, and z is equals to location parameter. So the location parameter comes as the deviation with our variable x. Mean is equals to b into gamma of this 1 plus 1 divided by a, and variance is equals to b square into the gamma value of 1 plus 2 by a minus gamma value of 1 plus 1 by a, and it's a square, where gamma z is equals to the we integrate it from 0 to infinity, t to the power z minus 1, e to the power minus t. We integrate it with respect to t. Gamma z is equals to z minus 1 factorial. We have seen it in our example as well, and this can be further written as z minus 1 into gamma z minus 1. So we calculate the PDF by a divided by b into x divided by b to the power a minus 1, and e to the power minus x divided by b to the power a for x is greater than equal to 0. Similarly, the CDF is equals to 1 minus e to the power minus x divided by b to the power a for x is greater than equal to 0. Now let us calculate the CDF of Weibull distribution and see some of the examples. Weibull, this is the Stata function to calculate the CDF of the Weibull distribution, while beneath it is the generic formula. So Weibull Stata function, it accepts the parameter a, b, g, and for the value of x we have kept the location parameter g as 0, and its generic formula 1 minus e to the power minus x divided by b to the power a, and let us see both of them should yield the same result. So the probability of getting less than or equal to 0.4, it is 28%, and let us see it by the help of graph. It is 28%, 28% somewhere over here, and the probability of getting less than 0.4. So the graph with the red line, it represents Weibull distribution, while the graph with the dash blue color dash line, it represents the Weibull proportional hazard. Now let us repeat the same process but with a different parameter. Say parameter is 3 and our scale parameter is 9 and the location parameter is 0 when the value of x is 75. So 7.5, the probability of getting less than equal to 7.5, it is 44%, and let us see whether we get the same result. 44% for 7.5, less than equal to 7.5, it is 44%. Now let us see another example. Our shape parameter is 9 and scale parameter is 15, location parameter is 0, and the value of x is 12.5. So the probability of getting less than equal to 12.5, it is nearly 18%, less than equal to 12.5, 18%. 12.5 less than equal to it, it is 18%, somewhere over here. Now let us see some more examples of the Weibull CDF for different parameters, and the red line, it indicates the CDF of the Weibull distribution, while with the dotted blue line, it represents the CDF of the Weibull proportional hazard distribution. Now let us see the CDF for these parameters. 0.5 and 0.5 is shape and scale. Location parameter g is equals to 1. All the three parameters, their value is 1. So the Weibull and Weibull proportional hazard distribution, the CDF, they have coincided for these parameters. And let us see what does it look like for this parameter. Here the shape parameter is 0.8 and scale parameter is 10, location parameter is 0, and for these parameters we get this kind of CDF graph. For positive location parameter, the graph is shifted towards the right, and we get this kind of CDF graph for the given parameters. Now let us explore the PDF of the Weibull distribution, and the first function Weibull den. This is our Stata function to calculate the priority for the Weibull distribution, and by the help of priority we will construct the PDF Weibull den, and the parameter a is equals to 5, b is equals to 4, and j is equals to 0, x is equals to 3. Beneath it we have its generic formula, a divided by b into, this is our x, divided by b to the power a minus 1 into e to the power minus x divided by b to the power a. And both the Stata function as well as the generic one, they should give the same result. So the probability of getting exactly 3 is 31%, and we should get the same result exactly 3, it is 31%. So exactly 3, it is 31%, somewhere over here. And again, the graph with the blue color, it is our proportional Weibull proportional hazard distribution PDF, and with the red color it is our Weibull distribution, the PDF of the Weibull distribution. And at the backdrop we have a normal distribution with the mean and variance equal to the mean and variance of this Weibull distribution. Now let us see another example. For the shape parameter is 3 and the scale parameter is 1.2, location parameter is 0, and the value of x is 1.25. Both the formulas should yield the same result. It is 87%, nearly 88%, and let us see it by the help of the graph as well. 87% and 1.25, it is 87%, somewhere over here. And let us see another example. For the shape parameter is 9 and the scale parameter 1 and the location parameter 0, and the value of x is equals to 1. The probability of getting exactly 1, it is 3.31, and let us see whether we get the same result by the help of the graph. 3.31, when it is 1, it is 3.31, somewhere over here. And when shape parameter a is equals to 9 and scale parameter b is equals to 1, we see that the Weibull distribution and the Weibull proportional hazard distribution, they are converging. And at the backdrop we have a normal distribution with the mean and variance equal to the mean and variance of the Weibull distribution. So the PDF of the Weibull distribution, when our shape parameter is 0.5, scale parameter is 1, and location parameter is 0, we get this kind of PDF graph. Shape parameter 1, scale parameter 1.1, and location parameter 0, we get this kind of graph. And the shape parameter is 2, scale parameter is 1.1, location parameter is 0, we get this kind of graph. The red one, it indicates the Weibull distribution, while the graph with the blue dash line, it represents the Weibull proportional hazard distribution. Shape and scale parameter is 3 and location parameter is 5. This one is the normal distribution. With the red one, it is our Weibull distribution, and with the blue dash line, it is our Weibull proportional hazard distribution. Again, the shape and scale parameter is 3, but the location parameter is 0. So in this case, the normal distribution and the Weibull distribution, they are nearly converging. So the PDF of the Weibull distribution for these parameters, the shape parameter is 5 and the scale parameter b is equals to 3, location parameter is 0. Shape parameter 5 and the scale parameter is 1, and the location parameter is again 0. Weibull distribution and the proportional hazard Weibull distribution, they have converged. And for this parameter, 7 is the shape and 1 is the scale parameter, we get this kind of graph. And when our shape parameter is 9 and the scale parameter is 1, we get this kind of graph. Similarly, our shape parameter is 9 and the scale parameter is 5, and location parameter is 1, we get this kind of graph. And shape parameter is 9 and our scale parameter is 1 and the location parameter is 0, we get this kind of graph. Now let us run some simulation. We will increase the shape parameter. We will increase the shape parameter from 1 to 4, while the scale parameter is 2 and the location parameter is 0. Let us repeat the same process, and this time the shape parameter is going to increase from 5 to 10, while the scale parameter is 5 and the location parameter is 1. Let us repeat the same process and increase the shape parameter from 4 to 10, while our scale parameter is 10 and the location parameter is 1. And one last example, let us again increase the shape parameter from 10 to 15, while the scale parameter is 15 and the location is 1. Now let us increase the scale parameter. So the shape parameter is 0.9 and we are going to increase the scale parameter from 10 to 15, while the location parameter is 1. Again, the shape parameter is 1.5 and we are going to increase the scale parameter from 1 to 5, while the location parameter is 1. Increment of shape parameter is actually increasing the variance, which is clear by this graph as well. And let us now keep the shape parameter is 2 and increase the scale parameter from 1 to 10 while the location parameter is 1. So with the increase in the scale parameter, the variance is increasing. For the shape parameter 3, and we want to increase the scale parameter from 10 to 20 while the location parameter is 1. And for the shape parameter is 4 and the scale parameter we are going to increase from 20 to 25 while the location parameter is 1. And as you know, increment of the location parameter is simply going to shift the graph. It is some sort of translation. Let us repeat the process, and our shape parameter is 3, scale parameter is 5, and we are going to increase the location parameter from 5 to 10. And let us see the PDF of the Weibull distribution when the shape parameter is 5 and the scale parameter is 9, and we are going to increase the location parameter from 8 to 18. Now let us see the area graph, and it is useful for one-tailed hypothesis testing. Weibull area, this is the Econometrics malware program. So the shape parameter is 2.1, scale parameter is 0.9, and location parameter is 0. Our value of x is equals to 1.8. This is our null hypothesis, and two alternative hypotheses: x is less than 1.8, left tail test, and x is greater than 1.8, it is our right tail test. So for the left tail test, it covers 99% of the area of this Weibull distribution. That is why we fail to reject the null either for the significance level of 5% or 1%, and we conclude that the value of x is 1.8. But for the right tail test, the probability is nearly 2%, p-value is 2%. So based on the significance level, we either reject or fail to reject the null. If our significance level is 5%, then our p-value is quite less than our significance level. In that case, we reject the null and we conclude that the value of x is greater than 1.8. But if our significance level is 1%, then in that case, the p-value 2% is greater than our significance level. In that case, we fail to reject the null and we conclude that the value of x is 1.8. Now, if a process follows a Weibull distribution and with a shape parameter 1.2 and scale parameter 1, and we want to test the hypothesis whether x is equals to 3, one tail test. So the null hypothesis, x is equals to 3, and our alternative hypothesis, x is less than 3 or x is greater than 3. Again, our left tail test, the p-value is 98%, which is greater than our significance of level of either 5% or 1%. In this case, we fail to reject the null and we conclude that the value of x is equals to 3. Again, for the right tail test, the p-value is nearly 2.4%. Again, depending on the significance level, we either reject or fail to reject the null. If our significance level is 5%, then in that case, p-value is quite less than our significance level. That is why we reject the null and we conclude that the value of x is greater than 3. But if the significance level is 1%, then in that case, p-value is greater than our significance level. In that case, we fail to reject the null and we conclude that the value of x is equals to 3. Now let us see another variation, and if a process follows a Weibull distribution with a shape parameter 3 and the scale parameter also 3, and we want to test the one tail test whether the value of x is equals to 0.7. This is the graphical representation of that situation. Our null hypothesis, x is equals to 0.7, and the alternative hypothesis whether x is less than 0.7, it is our left tail test, and x is greater than 0.7, it is our right tail test. Again, for the right tail test, we fail to reject the null either for the significance level of 5% or the significance level of 1%, because the p-value is quite greater than our significance level, and in that case we conclude that the value of x is 0.7. But in the case of left tail test, the p-value is nearly 1.3%, and if our significance level is 5%, then the p-value is quite less than our significance level. In that case, we reject the null and we conclude that the value of x is less than 0.7. But if our significance level is 1%, then in that case, p-value is greater than our significance level. So we fail to reject the null and we conclude that the value of x is 0.7. It is that simple. Now let us see one last example, and if a process follows a Weibull distribution with the shape parameter 12 and scale parameter 1.2, and we want to test a one tail test whether x is equals to 1.2. This is the graphical depiction. Our null hypothesis, x is equals to 1.2, and we have the alternative hypothesis, left tail test, x is less than 1.2, and our right tail test, x is greater than 1.2. And graphically it is very clear that the p-value for either of the cases, it is quite greater than our significance level of either 5% or 1%. So in this case we fail to reject the null and we conclude that the value of x is in fact 1.2. Now let us see the CDF and PDF of the Weibull proportional hazard distribution. First the CDF. So the CDF of the Weibull proportional hazard distribution for the parameter a is equals to shape parameter 0.3, scale parameter 1 and the location parameter 1. Now let us repeat the same process for these given parameters, and our shape parameter is equals to 1, scale parameter 1.3, location parameter 5. This is the CDF of the Weibull proportional hazard distribution. And when the shape parameter is 3, our scale parameter is 1.1 and location parameter is 1, we get this kind of CDF of the Weibull proportional hazard distribution. Now let us see what does the PDF look like, and we are going to draw the PDF of the proportional hazard Weibull distribution. A is 0.5 and B is equals to 1, location parameter is equals to 1. Now let us repeat the process. Our shape parameter is 0.5, scale parameter is 1, location parameter is 1. We get this kind of graph, the PDF graph of the Weibull proportional hazard distribution. And when all the parameters are 1, we get this kind of PDF of the Weibull proportional hazard distribution. And the shape parameter and the scale parameter are 2, while the location parameter is equals to 1. This we get this kind of PDF. It is actually the PDF. Here we have some error over here. And again the shape parameter and the scale parameter, they are equal to 3, while the location parameter is equals to 1. We get this kind of PDF, nearly a bell shaped. It is again the PDF of the Weibull proportional hazard distribution. This is an error. Now one last example, and the shape and scale parameter are 4 and the location parameter is equals to 1. We get nearly a bell shaped. So this is a Weibull proportional hazard probability PDF, probability density function. So it seems that for higher but equal value of shape and scale parameter, that is going to result in more bell shaped Weibull proportional hazard PDF. Now let us see some of the uses of the Weibull distribution. First of all, we are going to run the Weibull regression, proportional hazard Weibull regression. So Weibull proportional hazard regression, which we will explore or explain in detail in some other videos. Now let us see some of the usage of the Weibull distribution. It is used to model the time to failure of mechanical and electrical components, as well as the lifetime of biological systems. It is used to model the wind speed and wind energy potential at different locations. It is used to estimate the probability of failure for a given time period and can be used to calculate the failure rate of a system. It is used in extreme value analysis to model the occurrence of rare events such as floods, earthquakes, and landslides. It is used in material science to describe the strength and toughness of materials and to estimate the probability of failure under different loading conditions. It is used to model the probability of extreme weather events such as heavy rains or snowfall and to make predictions about the likelihood of such events. It is used to model mortality rates and life expectancy and can be used to make predictions about population growth and aging. It is used in finance to model the stock price, interest rate, and other financial variables. Similarly, it is used in medical research to model the distribution of disease progression and treatment response. Similarly, it is used in many other fields like telecommunications, environmental science, sports, and physical performance, as well as industrial process, and so on. So this is it for this tutorial. Thank you very much for your time. Thank you very much, Econometrics Melody.